Welcome back, folks. In this video, we'll be talking about vectors part 2B, because we've talked about. Okay, so with this question, we're going to look at this boat. He is heading straight across the water. I'm going to label this as V with a subscript of BW. And I'll talk about that down here, because really what we're going to do is we're going to look at the velocity of this boat, hence the B, relative to the water. Okay, another way that this is saying, or letters that are used to describe this is the velocity of the boat with respect to the water. Okay, so this is just, it's also known as how fast can the boat move in still water. Okay, so, and then we would represent the velocity of the water relative to the ground, velocity of the water relative to the ground, and that's going to give us the resultant velocity of the boat. Okay, and the resultant velocity of the boat is going to be what you would see if looking from shore. So this is the velocity of the boat relative to the ground. Okay, so it's kind of messy and I don't know how clear that is, but really we're looking at, hey, a boat that's pointing straight across the river, he's going to end up downstream or upstream, depending on how much current is being affected on this thing. Okay, so there's a application or a sim that you can go and check out if you just Google physics classroom riverboat. Down here, if you just go launch interactive, you'll be taken to this screen. The physics classroom is a pretty awesome resource for all things physics. The riverboat simulator, I'm going to go and just make this thing into full screen. And here we are looking at a river where this boat is going to try and get across it. If I hit play, you can just see what's happening. Okay, this boat is trying to get across the river. This time our river is pointing downstream. And we can do a whole bunch of things with this. We can look at how far the boat goes horizontally. I'm looking at the bottom of the screen. How far downstream this boat ends up, or vertical displacement. Okay, we can also look at how much time it takes for this boat to cross the river. Okay, and we can change some things. We can make the boat go faster. We can make the river speed go faster. So now if I click play, hey, the river speed's a little bit higher. This thing's going to be moving even further downstream. So I'm going to skip back to our question, or sorry, to our notes here, and I'm going to kick to the next slide, and it's going to be a question. Okay, so take a moment and jot this one down, please. Okay, the first thing I'm going to do in this question is try and get myself a picture for what is happening. So we've got a motorboat that's heading 8.5 meters per second in still water. It's going to head straight east across a river. So here's our boat. It's going to head straight east across a river. And that river is, I'm just going to put the displacement of this river is 110 meters wide. Okay, so the water is flowing downstream, so I should probably make this blue because it's water. Water is flowing downstream. I'll represent that water with an arrow going downwards, and that velocity of the water is going to be 3.8 meters per second. What is the boat's resultant velocity? Well, we're going to draw a resultant just like we've been doing for all of our vector questions. So the resultant velocity will be pointing like so down the river. So if the water flows, I'm looking at question A, if the water flows downstream at a rate of 3.8 meters per second, what is the boat's resultant velocity? So we've got a triangle. Just to clean this up, I'm just going to redraw a triangle where we have our 8.5, 3.8, and then I'll also just label this theta. So in this question, we're going to have r squared is equal to 8.5 squared plus 3.8 squared. Okay, I can work this through to find that my resultant after I plug and chug is going to be 9.3 meters per second. The angle theta, I'm going to use tangent. Theta is 3.8 over 8.5. Okay, my angle then ends up being 24 degrees. Okay, so for question A, the answer to this would be 9.3 meters per second at a direction of 24 degrees south of east. Okay, that's for part A. How long, so question B, how long does it take the boat to reach the opposite shore? Okay, so this is a constant velocity problem where we are going to look at how long or how much time does it take the boat to get across the river. Now, I'm going to take this 110 meters at the top. I'm going to just draw that as a displacement vector because that is how far across the river is. So I'm going to put little vector hats on here just to remind myself that if I use 110 meters, and I want to because I want to know how long it takes to reach the opposite shore, 110 meters, well, which velocity number do I use? I have to use the 8.5 meters per second because that is the component of this boat's velocity that is moving horizontally across this river. Okay, so if I go and just plug and chug that, I should get a time of 12.9 seconds or 13 seconds to get across this river. Okay, how far downstream? Question C, how far downstream does the boat end up? So that's looking at, hey, displacement. It's another constant velocity question where our displacement in the up and down direction or the north-south direction is going to be affected by the velocity in the y direction, which in our case is the velocity of the water. So 3.8 meters per second times a time of 12.9 seconds and our displacement downriver, we would end up 49 meters downriver. Okay, so at the risk of using, a bad word, this is a dumb boater. The boater ended up 49 meters away from where he wanted to. He wanted to end up across the river, and he ended up a little bit downstream. So let's look at what a smart boater would do. So if we had the same motorboat, and this same motorboat wanted to end up directly east of where they started, they're going to need to point the boat. They're going to need to point the boat upstream. So again, if we have our boat starts here, we're going to need to point this boat upstream, and the boat is still going to only be able to travel at 8.5 meters per second. It's only going to be able to travel 8.5 meters per second, and it's going to aim a little bit upstream because that current will push that boat downstream so that at the end of the day, they are ending up straight across the river. So the resultant in this case is the vector that's pointing straight across this river because this boater is smart. Put an angle theta in there. So the resultant in this case, the change here is that our resultant is no longer the hypotenuse of our triangle. Okay, so what direction should the boat head? So I'm going to look at the two letters that I'm going to put on here, O and H, because 3.8 meters per second, that is the side that is opposite theta. We are given 8.5, which is our hypotenuse. So in this case, the sine of angle theta is 3.8 over 8.5. Okay, if I go and plug and chug this, we should get the sine of theta is 0.447. If I take the inverse sine of both sides, we should get an angle that this boater should be pointing at. The angle should be 26.55 degrees or 27 degrees. Okay, what is the resultant velocity of the boat? Part B. Part B is saying, okay, well, this is using Pythagorean theorem, only in this case, our resultant velocity of the boat just happens to not be the hypotenuse. So we'll solve this in a little different way. We can plug and chug to find that r squared is going to be equal to 57.81, or the resultant velocity would be 7.6 meters per second, and this velocity would be directed exactly east because this boater is smart. Okay, how long would it take to cross the river? How long is a time question where we have what's the displacement over the velocity? In our case, our displacement vector, reminder, our displacement vector is that 110 meters that's pointing directly across the river or pointing to the east. So if we're using 110 meters in this equation, we have to be using the velocity vector that is pointing in the same direction. So in our case, that's the one we just solved for, 7.6 meters. Whoops. So our time to get across this river would be 14.5 seconds. Okay. Let's look at airplanes. Airplanes behave in a similar fashion as boats do, where instead of current, they have wind. So in this case, we'd have, I'd say that this plane has a headwind. And in the far, we'll even write no wind. We'll even write no wind here. So, and on the far right example, we'd end up with a plane that has, this is the velocity of our plane. Okay, that's velocity of our plane. And we usually write that as plane relative to the air. And then we'd have the velocity of the air relative to the ground. That'll give us a resulting path or a resultant path of the plane relative to the ground. Okay, so if I write those things out, I'm going to use some other words here. So that's the velocity of the plane relative to the air plus the velocity of the air relative to the ground is going to give us our resultant velocity of the plane relative to the ground. Okay, and then if we go and add some extra words here. So normally what we call this first one, the plane relative to air, this is the airspeed. That's the airspeed of an airplane. It's what it's designed to fly. Okay. The other thing we call the velocity of the air relative to the ground, we call that wind speed. Okay. Pilots always have to account for the wind that is trying to blow them off course. Okay, and lastly, velocity of the plane relative to the ground. We call that ground speed. Just some technical terminology for you future pilots. Okay, I'm also realizing that I made a mistake earlier in this slide. I said that this first plane has no wind. Well, that is incorrect because when you look at the bottom of the screen, that plane in your left-hand column, that's beating, it's faster than the plane all the way on the right. So this thing actually has a bit of a tailwind. So this is a tailwind. It's pushing that plane a little bit faster, which happens with airplanes all the time. You're traveling from west to east, like a plane ride from Vancouver to Toronto is generally quicker than a plane ride from Toronto heading west out to Vancouver because planes get to catch that tailwind that is primarily flowing from west to east above Western Canada. Okay, let's look at a question. You, who is a smart pilot, want to fly a plane directly east to Toronto, a distance of 3,925 kilometers. The plane can fly 650 kilometers an hour in still air. There's a wind blowing from the north. Find a few things: speed of your airplane, direction you want to point, and the time it will take to get to Toronto. First of all, I'm going to draw a picture. I want to get a handle on what this thing is asking. So here's our start. Here's our finish. Okay. I know that as a smart pilot, this is what I want my resultant to be. That's my R. I want to end up going directly east. Okay, so if I've got a plane that's blowing from the north towards the south, I'm going to have to aim this plane little bit north, right? Because this wind is going to be pushing at 150 kilometers per hour. I'm going to need to aim this plane north of where I want to end up so that I actually end up in Toronto and I don't end up in the United States of America. Okay, so I'm going to put an angle theta on here just so we'll have an angle to talk about. So we've got our triangle to work with. So the speed of your airplane relative to the ground, or your ground speed, is going to be this R value. So in part A, we'll apply Pythagorean theorem. We'll say that 650 squared, which is our hypotenuse, is going to be 150 squared plus our R squared. Okay, if we work through some math, we'll get our R squared is equal to 400,000, or R is equal to 632 kilometers per hour. Okay, the direction that we're going to point the plane, okay, the direction that we will point the plane, we'll use 150 divided by 650 will be equal to the sine of angle theta. Okay, so that means to find theta, we'll have to do the inverse sine of 150 over 650, or the inverse sine of 0.23, which gives us an angle of 13 degrees. Okay. Lastly, time it will take to get to Toronto. Time is going to be displacement divided by velocity. Our displacement is due east, so 39.25 kilometers. Okay, the velocity that is heading straight to the east is going to be that resultant velocity that we found, or 632 kilometers per hour. The time that this plane will take to get from west to east will be 6.2 hours. Okay, smart pilot ends up in Toronto, not in the United States. Okay, can you please, there are 4 questions remaining on worksheet number 1. 2 of them are boaters, 2 of them are airplane pilots. Please give those a try. Let me know if you have any questions, and we'll see you the next time.